Welcome to Exploiting the Hyper-V IDE Emulator to Escape the Virtual Machine in Lagoon JKL with Joe Bialek. Before we begin, a few brief notes. Please stop by the business hall located in Mandalay Bay, Oceanside, and Shoreline ballrooms on level 2 during the day and for the welcome reception at 5:30 p.m. tonight. The Black Hat Arsenal is in the business hall on level 2. Please join us for the Pony Awards in Lagoon JKL, which is this room, at 6:30 p.m. And lunch is in Bayside AB from 12:05 to 1:30. Please put your phones on vibrate. It makes it easier for the rest of us to ignore the ringing while you wait for your voicemail to pick it up. Now please give a warm welcome to Joe Bialek.
Hi. So my name's Joe, and I work for Microsoft on the MSRC Vulnerabilities and Mitigations team. And in case you haven't noticed, Microsoft cares quite a bit about Hyper-V. And we've actually paid out $625,000 in Hyper-V bounties since Black Hat last year. Today I'm going to be talking about exploiting a vulnerability that was reported to us through the Hyper-V bug bounty, and also show you how incredibly impactful some of the bug reports that you send to us can be. So this story begins sometime in 2017, and I was going through a number of the Hyper-V emulators at the time and looking for security bugs. I started reviewing the emulated storage stack, and as you might expect from code that's written in the 90s, some of the code in here was a bit sketchy. Just as a quick example, there was this function. It was called writeDataPort, and the thing that had me a little bit concerned about this function was that there was a memcopy happening with a pointer that it had a bunch of arithmetic done on it, and it seemed like some of the arithmetic was checked, and some of the arithmetic definitely was not checked in this function at least, but other parts of the state machine, in theory, were supposed to be validating that none of these offsets would ever force the buffer to go out of bounds. Now, unfortunately for me, I did not end up finding a way to trigger a bug here because I got sidetracked. We had a meeting with the Visual Studio team at Microsoft, and they were talking to us about this class that they were helping create for C++ called the span. And really all that a span does is it wraps an array. So it has a pointer, it has a size, and whenever you do array accesses, it does bounds checking for you and fast fails if you're doing an out of bounds access. Now, one of the things that we're pretty interested in is how we can make our product safer and just eliminate classes of vulnerabilities. So this seemed pretty cool to us. And I ended up switching gears and porting GSL span into the emulated storage stack because it seemed like a good candidate based on what I had seen. And as I was wrapping that up, a crash dump appeared on my desk. A researcher that I was working fairly closely with at the time sent me a crash dump just as a friendly heads up and told me that he would send me a POC shortly and maybe even work on an exploit. Now, I didn't want to wait for a POC because this seemed pretty cool. He had a crash in Hyper-V. And so I cracked open the crash dump. And lo and behold, the crash dump is actually in the emulated storage component, which I've been working on. And actually, the crash dump is inside of this writeDataPort function, which looked questionable to me. And when I went and looked at what was going on in that function, there were a couple interesting things to me. There was a buffer here. It's called the track cache buffer, and it's 64 kilobytes big. And there's another variable called the drive state buffer offset. And this variable ends up getting added to the track cache buffer. But this offset was way bigger than 64 kilobytes. And so it appeared that this arithmetic that was being done on the pointer probably wasn't correct after all. Now we're going to talk more about this in a second, but before we talk more about it, I want to give you at least some understanding as to what this component is and where it lives. Nico and I gave a talk at Black Hat last year about Hyper-V architecture, so if you want to know all the gory details, you should check that talk out. For the purposes of this talk though, what you need to know is that Hyper-V is Microsoft's bare metal hypervisor. In Hyper-V, we have this concept of partitions, and that just enforces isolation between the different virtual machines that are running on the system. The hypervisor will enforce that different virtual machines cannot interact with each other's physical memory using extended page tables. And the hypervisor will intercept attempts to execute certain instructions, like the in and out instruction, which is used to talk directly to hardware over I/O ports. And if you try to execute some of those instructions, then the hypervisor will just emulate them instead, so that you can't end up doing harm to other virtual machines running on the system. In Hyper-V, we do have one special partition, and that's called the root partition. and it's where the host operating system lives. The host operating system is effectively responsible for managing all the virtual machines that run on the system. And one of the things that it does is it provides device emulation to those virtual machines if they need it. And that brings us to the IDE emulator or the emulated storage component. I use both of those interchangeably. What this diagram shows is that when the guest operating system goes and executes an in or out instruction to do an I/O port read or write, that will be intercepted by the hypervisor. The hypervisor will forward that down to the host operating system's kernel, and the host operating system's kernel will forward that down to the VM worker process. Now there's one VM worker process for every virtual machine running on the system. And that actually provides one really nice property for us, which is that if you find a bug in code in the worker process that just allows you to crash the worker process, that vulnerability only allows you to create a denial of service for your own virtual machine. It doesn't actually impact anything else running on the system. Now, the VM worker process is where a number of components live. One of them is the instruction emulator, which is responsible for decoding this I/O port read or write instruction and determining what exactly you're trying to do. And then the instruction emulator will end up forwarding that on to the appropriate device emulator. In this case, we can assume that it is going to the emulated storage device emulator. And this consists of a couple components. There is the IDE controller device. There are 2 IDE channels that are attached to that controller device, and each channel has 2 attachments attached to it. And those attachments can either be hard drives or optical drives. For the purposes of this talk, I'm going to be using hard drives. And also for the purposes of this talk, the only I/O ports that actually matter are 1F0 through 1F7. The emulated storage component does emulate a number of other I/O ports, but they don't matter for this vulnerability. Let's talk more about the bug. So as I mentioned, I was already working on the emulated storage component when this crash dump was sent to us. And rather than wait for the POC to come, I decided I couldn't wait, and I wanted to try to figure out what was actually going on here. It was a little bit of a point of pride for me because I had clearly missed this bug when I had first looked at the function. So I spent about half a day trying to figure out how I could force this condition to happen, and after about half a day, I had a POC created. The vulnerability itself is inside of the state machine of the emulated storage device. So it's not super straightforward to show you like a code snippet for like, here's exactly where the bug is. But effectively what was happening here is that the emulated storage component was supposed to enforce that this drive state buffer offset variable would never get too big, and it wasn't enforcing that correctly. So the way that you trigger the bug is first you do a couple of I/O port writes just to put this device in a desired state. And then there's this loop here, and it's in dark blue. I can try to highlight this with my laser pointer. This loop right here, every time this loop executes, it does an I/O port write, and every I/O port write that you execute there will end up incrementing the drive state buffer offset by 512. So the drive state buffer offset is always 512 byte aligned. Now there's 2 ways you can go. The first way you can go is you can issue an I/O port write to port 1F0, and when you do that, that is going to trigger a write to the track cache buffer using this massive drive state buffer offset. So you have an out of bounds write. The other way you can go is you can do an I/O port read from that same I/O port. And when you do that, it will trigger a read from the track cache buffer, and it will return that data to you. And you have an out-of-bounds read there. If we look at the functions that are actually involved, and this is probably too small to read, but I'm just going to talk through it, and you can reference the slide later if you want to. There's this function inside the emulated storage component, and it's called write data port. And this function has a couple of key variables. It has the track cache buffer, which is this pointer. It has the drive state buffer offset, which is this value that we can increment to be out of bounds. And that is a unsigned 32-bit value. So you can increment that value to be up to 4 gigabytes big. And the other important variable here is this current byte variable. And this is always between 0 and 512. Gets incremented every time you read or write from the track cache buffer. And once it hits 511, it will reset back down to 0. Now what this function ends up doing is it adds these variables together, the buffer, the drive state buffer offset, and that current byte, and it uses that as the destination for a memcopy. And the source of the memcopy is the attacker controlled data that was specified to be used in the IO port write. So you have a relative write primitive here with a attacker controlled 32-bit offset and attacker controlled data. And just in case it isn't super clear, the way that you end up having that full 32-bit offset under your control is the high 23 bits come from the drive state buffer offset, because that's always going to be 512 byte aligned, and the low 9 bits come from the current byte. Now there's a corresponding function here. It's called read data port. It pretty much does the opposite thing. It uses those same 3 variables to compute a pointer, but instead of writing to that pointer, it reads from the pointer. And it copies that data into a buffer, which will eventually be returned to the guest. So this gives me a relative read primitive with a controlled, unsigned 32-bit offset. And one thing that was cool and a little bit unfortunate was that that version of the emulated storage stack that I had been porting GSL span into was not actually vulnerable to this bug, because as soon as you run the POC, the VM worker process would just immediately fast fail. It would never let you go out of bounds, and you would just crash your own virtual machine, and nothing else on the host was impacted. But of course, we hadn't shipped it yet. In fact, I don't even think it had been checked in yet, so that doesn't do us any good quite yet. But it is still kind of interesting for us to see that proactive work we were doing was actually killing real bugs that people were finding. So let's move on. This bug looked awesome. It's, I have this 32-bit index that I control and I can read and write. And so I figured I'd like to try to write an exploit for it. And I figured I'd start with Server 2012 R2 because it was being used in cloud environments, and also because I figured it would be easier than exploiting the latest version of Windows. So it would be a little bit of a warm-up for me. I had a few constraints with writing this exploit. The first constraint is that the emulated storage path is slow, and the way that I had written my POC made it even slower than it needed to be. And so I figured that if the way that I was going to exploit this bug required me winning some weird timing or race condition between threads, that's probably not going to be practical. I'm also limited to only using Generation 1 virtual machines. Hyper-V has 2 generations of virtual machines. The emulated storage stack is not supported on the 2nd generation. And really all that means is that I have a more limited set of devices that I can use to try to do things like heap massaging or build other primitives out of. And of course, the VM worker process is running with control flow guard and ASLR and DEP enabled. And it is only a 64-bit process. You cannot have a 32-bit Hyper-V host, so the VM worker process will never be 32 bits. And that's a little bit unfortunate for me, because if it was a 32-bit process and I have a full control over a 32-bit unsigned index, then I would just immediately have a full read-write primitive over the entire virtual address space of the process. But that's not the case here. So the first question that I had is, where does the track cache buffer get allocated? Is it in the heap or is it somewhere else? And it turns out that it is allocated using the VirtualAlloc API, which is a bottom-up allocator in Windows. And the allocations that are returned by VirtualAlloc are always 64 kilobytes aligned, and they are made sequentially to reduce fragmentation in the virtual address space. So I have a little example here on the side where if you go and you make a whole bunch of VirtualAlloc allocations, you will see that the address just grows 64 kilobytes at a time. Or if the allocation is bigger than 64 kilobytes, then it grows by a larger amount at a time. But they're all sequential. And this gave me an idea, which is that it might be possible that there is some interesting buffer that is allocated at some predictable offset from the track cache buffer. Because these allocations are all made in such a sequential and predictable way. However, it's not guaranteed that that's going to be the case, because if there's multiple threads calling VirtualAlloc at a time, then there can still be unpredictability in how things are laid out. So what I did to figure out if this was the case or not is I just started turning virtual machines on, and then I would use VMMap to go and dump the address space of the VM worker process. And I did this over a whole bunch of reboots, and every time that I would do it, I would record what I was seeing, and I created this memory layout generalization based off that data. And there are a couple interesting things here that I noticed. So near the top, we have the track cache buffer. And after the track cache buffer, we had these allocations that I just refer to them as the miscellaneous allocations. And it seemed to be typically anywhere from 64 kilobytes to 3 megabytes. And this immediately kind of messes up my plan because none of these allocations looked like good corruption targets, and there was a totally variable number of them. After that, there was this buffer called the VRAM buffer. It's 8 megabytes big, and I'll talk more about that in a second. That was followed by a stack, and I call it the unreliable stack because it seemed to die a lot, and so I didn't really want to try to corrupt it because it would just unmap itself a lot of the times. Then there was a heap. It was 1,088 kilobytes. It had a single allocation in it. It wasn't a good corruption target. There were a couple small allocations, and then there was this floppy device event listener stack. And one key observation I had here is that there seems to be a fixed offset between the end of that VRAM buffer and the start of the floppy device event listener stack. Now I was thinking that corrupting a stack would be great because if I corrupt a stack, then I can just ignore control flow guard since it doesn't actually protect stacks. But the issue is that there's no predictable offset between that track cache buffer and any of the stacks on the system because of these miscellaneous allocations that vary in size so much. So I really needed to figure out if there was a reliable way that I could read and write stacks. So I started looking at this VRAM buffer to figure out what it was. And it turns out that this is what is known in Hyper-V lingo as an aperture. And all that an aperture is a shared section that maps guest physical memory. And I'm of course running in the guest, so I can go and write whatever I want in that physical memory. And whenever I write data into that physical memory, it immediately shows up inside of this VRAM buffer in the VM worker process. So here's what I did. I went and wrote a bunch of markers inside of that VRAM buffer, and every marker just tells me how much of the VRAM buffer is left. And you'll see why this is useful in a second here. The next thing I noticed is that since those miscellaneous allocations never seemed to be bigger than 3 megabytes, but the VRAM buffer is 8 megabytes big, I could just index 8 megabytes off the end of that track cache buffer, and I would land somewhere in the VRAM buffer. Now I have no way to know exactly where I'm going to land in it, but I will land somewhere in it. And so what I can do here is I can use my out of bounds read and go and read 8 megabytes off the end of that buffer, and then read the marker that I wrote into the VRAM buffer. And that will tell me how far into the VRAM buffer I am. Once I know how far into the VRAM buffer I am, I know how much further I need to read out of bounds to get to the end of that VRAM buffer. And this gives me pretty much everything that I need to exploit the bug, because there seemed to be a fixed offset between the end of the VRAM buffer and the start of the floppy device event listener stack. So once I find the end of the VRAM buffer, I now also know how far I need to read and write out of bounds to get to that stack. And so I can go and I can read from the stack and leak the address of NTDLL and kernel 32. And then I can go and I can corrupt that stack and write a ROP payload on it. There was one little remaining issue here, which is that the floppy device event listener stack needs to unwind before I can trigger my payload. And this stack was always just sitting waiting for events to be signaled to it. Now, nobody really uses floppy drives anymore, and the only way that it seemed that events would be signaled to this is if you had a floppy drive plugged into your virtual machine and it was doing things. But one thing I did realize is that if I restart the virtual machine, that will also signal the floppy device event listener stack, because it will tell that stack, hey, the virtual machine is shutting down, so the stack is going away. And that will trigger the stack to unwind, and that will then kick off my payload. I have a little demo here. The demos are all recorded because some of them take a little while to run. But effectively what I'm doing here is I'm running on a 2012 R2 host, and I have this guest operating system here. I run the exploit. The first thing that it does is go and look for markers inside the VRAM buffer. Now it's found the markers in the VRAM buffer, and so it's going to go and read from the stack, look for addresses, and then it's going to go and corrupt the stack with the payload that I've created. Now in this case, the payload is just going to call winexec to pop calc. So it's writing, it's writing. It takes a little while to do these writes, but it's now finished writing. And the exploit tells me helpfully that I now need to restart the virtual machine to actually trigger that payload. And so I go and restart. And then if you use Process Explorer, you can see that pop calcs, it's in session 0, so you don't actually see it on your desktop here. But we do pop calc, and it's running as the VM worker process's user account. So that's great. Oh. Alrighty. So then I decided to set my sights on something hopefully more challenging, which was the latest version of Windows at the time. Windows 10 1709. I believe the code name for this was Redstone 3. It was not quite released yet, but it was almost released at this point. So the obvious question is, what has changed, right? If I'm going after a new version of Windows, can I just do the exact same thing or not? Now, one big change that was made was as a result of an exploit that Jordan Rabet wrote, who's on the OSR team in Microsoft. Stacks, TEBs, and PEBs were no longer allocated anywhere near the rest of the bottom-up allocations in Windows, which means they are not allocated anywhere near any allocation made using VirtualAlloc. This means that I can no longer use my read-write primitive to read and write to stacks. So that immediately changes everything about the exploit effectively. We also have more exploit mitigations that are applied in the latest version of Windows. The VM worker process had ACG and CIG enabled. And these are just two mitigations that effectively make it so that the process itself cannot allocate its own executable code pages. And the only executable code pages that the kernel will map in are code pages that are signed by Microsoft. We also have no child process enabled, which means you can no longer spawn child processes. And we have another mitigation enabled, which prevents you from loading DLLs that are from a network location. And then we also have a number of control flow guard improvements that have been made. A lot of these were reported through the Hyper-V bounty, or sorry, not the Hyper-V bounty, but the mitigations bounty that we have. So we had done some work to harden CFG. But really the big thing here was that since stacks were no longer allocated near me, I was going to have to change a lot about how I exploited this bug. So I ended up doing the same initial process of using VMMap to go and create this memory layout generalization. And a lot of it was the same. There were a couple important things though. One important thing is that most of the heaps in the VM worker process are allocated at a lower virtual address than the track cache buffer. And that means I cannot read or write them. However, there was this one heap that I am going to refer to as the target heap for the purposes of this talk. It was a 4 megabyte heap, and I could read and write that from the track cache buffer using this out of bounds primitive that I had. And the other nice thing is that this target heap also seemed to be at a fixed offset from the VRAM buffer. Now, one thing that I quickly noticed was that I could use the exact same technique as before to find the VRAM buffer. Those allocations had not changed, so there was the track cache buffer, miscellaneous allocations, and then a VRAM buffer. So with this, I had a couple ideas for how I could go about exploiting the bug. The first thing that I really wanted to do was I wanted to find some interesting piece of data that I could corrupt so that I could boost my relative read-write primitive to arbitrary read-write. And my thought there was, if I can get an arbitrary read-write primitive, then maybe I can leak the address of a stack, and I could just go corrupt the stack again and completely ignore control flow guard. So that seemed great. The other idea I had was I could obviously go and just corrupt a function pointer, and then I would have to confront control flow guard head on. I would have to find some way to bypass it. But let's start with the first one, because that's what I really wanted to make work. The first thing that I did was I started logging all of the heap allocations that were being made by the VM worker process. So I would turn the virtual machine on, let it run, look at the call stack of all those allocations, and look and see if any of those allocations looked like they could be influenced by the guest, like if I could spray a bunch of allocations. And for any of those allocations, then I wanted to see, is there interesting data in them that if I corrupted, I could boost myself to this arbitrary read-write primitive. And sadly for me, this did not work out, because as it turned out, the VM worker process, for a generation 1 virtual machine at least, has effectively no ability to spray allocations on the heap. Almost all of the allocations are made up front when the virtual machine turns on, and so it was just a dead end. So I moved on, and instead I figured that I would just go and look at that target heap and see if there were any interesting allocations that were already allocated in the target heap that had a similar property of having some interesting piece of data that I could corrupt and then get an arbitrary read-write primitive. And one thing that I spent probably way too much time on, but I just wanted it to work so bad, was I wanted to find an emulator that had, like the class that implemented the emulator was allocated inside of that target heap. Because I figured if I did that, then I could go and just corrupt the buffer that emulator writes IO port writes into, or that it retrieves IO port reads from. So if I corrupted that pointer, then maybe I could just get arbitrary read-write to anywhere in the address space. But it didn't work out. The emulators were effectively never allocated in this target heap, so I couldn't corrupt the emulators themselves, and I wasn't able to find anything else in the target heap that looked like an interesting target for data corruption. Okay, so I ended up moving on. This didn't seem like it was going to work, so I figured that rather than do a data corruption, I was probably going to have to just go and confront control flow guard. But I figured maybe that would be easy. Maybe what I could do is I could go and just look at all the binaries that get loaded into the worker process, and I could find a binary that was not compiled with control flow guard at all. And if that was the case, then it would have a whole bunch of unprotected indirect calls. So that would make it hopefully pretty easy for me to bypass CFG. But I did not find any binaries that were not compiled with control flow guard. And I also wanted to see if I could just find some indirect calls, maybe indirect calls that were written with assembly that were missing control flow guard instrumentation on that specific indirect call. And once again, I hit a dead end here. I could not find any indirect calls that were loaded into the worker process that were missing CFG instrumentation. There were a couple of control flow guard bypasses that existed in some of these binaries. Some of them were publicly known at the time. However, all of the bypasses that I found either required that I knew the address of my current stack, which I do not, or they required that I had to win some race condition between two threads. So I had to get one thread to start executing down a code path, and then I had to do a write at like a very specific time to race what that thread was doing. And that just seemed completely impractical with the primitive that I had. So it looked like I wasn't going to be able to get a super easy control flow guard bypass. So I decided that rather than look for easy CFG bypasses, what I was going to do was just try to abuse the coarse-grained nature of control flow guard. And I was going to make valid indirect calls that just gave me a little bit more control over the address space of the process, maybe try to get a read-write primitive out of it. But in order to do this, I needed some building blocks. So I started looking around and just looking for things that looked interesting that I could use to start building an exploit. One of the first things I found was this class. It's called the VideoDirtListener. One really amazing thing about this class is that it's allocated in the target heap, so I can corrupt it. Great, that's like my first requirement, right? Another nice thing about this class is that it has virtual functions. Now, one downside is that those virtual functions are only triggered when the virtual machine reboots. So I once again have this situation where I need to reboot the VM to trigger things. But that's okay, I can work with it. Another nice thing about this class is that it has a very large buffer inside of it. It's over a page big. And that matters because when you reboot the virtual machine, a lot of the allocations that are in the heap have already been freed by the time virtual functions in this class have been called. And if you're going to try to execute some sort of payload, you need to be sure that your payload still exists when you go to execute it. So the fact that this class both had virtual function table and it had this massive buffer where I could store a payload was great. And then the other thing is that I can find the address of combase.dll and rpcrt4dll inside of the target heap. Unfortunately for me, I could not find the address of kernel base inside the target heap. And I'll talk more about why that matters in a minute. The VideoDirtListener object itself, it's actually pretty complicated. It has a lot of things, but for the purposes of this talk, there's only two things that matter. At offset 150, there's a vtable, and immediately following that vtable is this massive page size buffer that is completely unused during normal VM operation, so I am free to write whatever I want into it. The next building block that I found was this cool CFG gadget. I'm just going to refer to it as the looping indirect caller. There's this function, it's called revert changes. It is a valid indirect call target. So if you hijack a function pointer, you can call this function. What this function does is it takes a context structure, it follows a list head field inside of that context structure, and loops through a linked list of these node structures. On every node structure, it makes a virtual function call. It does not pass any parameters to the virtual function call except for the implied this pointer that is always passed to virtual function calls. And then it just keeps looping through the list. So this effectively gives me the ability to make an unlimited number of indirect calls. So what I can do here is I can have this VideoDirtListener object, and I can overlay this context structure into it, such that when the virtual function call is made on the VideoDirtListener, it actually calls this revert changes function, and that kicks off this loop where I get to make an unlimited number of virtual function calls. So that's great. I've kind of boosted my capabilities a little bit, right? Instead of only being able to make one virtual function call when the virtual machine reboots, I can now make an unlimited number. Unfortunately, I don't control the parameters of any of those virtual function calls, and so it's not super useful for me right now. But luckily for me, Thomas Garnier has already done some research in this area, and he found that there's this really interesting function in the RPC runtime of Windows called NDR Server Call2. And what this function does, it takes a single parameter, this parameter, and when the function is called, it will use that parameter to deserialize some data structures. And it will deserialize those data structures into the address of a function to call indirectly. Now this function needs to be a valid indirect call target, but it'll take that address of that function, and it will also deserialize a list of arguments. And you control the number of arguments and the value of the arguments. So what this means is that I have now a primitive that will allow me to loop through and make an unlimited number of indirect calls, but also, using this NDR Server Call2 technique, I can have full control over the number of parameters and the value of the parameters that are made to those function calls. And really what this diagram is just illustrating is that we have these node structures that we loop through, and we overlay an RPC message structure on top of it, which is the structure that the NDR Server Call2 function is expecting. The first parameter of both of these structures, the node and the RPC message, is a vtable, so that aligns well. And the only other parameter that actually matters in the node structure to do this looping through a linked list is a next field, which is at offset 58. But the RPC message itself is only hex 50 bytes big, which means that you can safely overlay these two structures and none of the fields conflict with each other. All right, the last gadget that I found that I needed was this MemCopy Gadget. This is once again a function that is an indirect call target, and it uses the parameters that are passed to it to make a call to MemCopy. And what this ends up giving me is an arbitrary read-write primitive, because I control the source, the destination, and the size of that call to MemCopy. However, there is this caveat that I can only, or caveat that I can only make this call to MemCopy when the virtual machine reboots. But I figure with this, I can probably get a working exploit. The strategy that I figure I'd use is, first I'm going to get this arbitrary read-write primitive, and I get that using this MemCopy gadget. Then I need to leak the address of kernel base, And the reason I need to leak the address of kernel base is because I want to call the function virtual protect. I'm going to use virtual protect to make the control flow guard check function pointer writable. This is the function that gets called every time you need to validate if some function is a valid indirect call target or not. So I make that function pointer writable, and then I overwrite it with a function that always returns, yes, this is a valid indirect call target. And then once control flow guard is effectively neutralized, I can make indirect calls anywhere I want. So I can make an indirect call to kick off a ROP chain. So that's exactly what I did. The first thing I need to do, of course, is I need to read the target heap, and I need to find the address of RPC RT4, comm base, and the VideoDirtListener object. And it's worth noting that while these offsets are typically fixed, so like the offset between the VRAM buffer and the target heap is typically fixed, it's not 100% of the time. So this will fail sometimes. And you know, the VideoDirtListener object itself is not always allocated in the target heap. And if it's not allocated in the target heap, then I need to restart the VM and try again. And every time I have to restart the VM and try again, that's just one more chance for this whole thing to fail, right? Because I'm going to have to go and refine the target heap, but it might not actually be there, and then I crash. So it's worth calling out that this is actually less reliable than the previous exploit. Anyway, so I find these addresses, and the next thing I'm going to do is I need to create this MemCopy payload so that I can have my arbitrary read-write. But there's a problem, which is that this is triggered when the virtual machine is rebooting, and the track cache buffer and the VRAM buffer are both going to be freed as part of the virtual machine rebooting. Most of the allocations in the target heap are going to be freed as part of the virtual machine rebooting. And I have no ability to interact with the VM worker process while that payload is executing, because when I restart the VM, all of the virtual processors of that VM are stopped. And so I just have to wait for this payload to execute, and then when the virtual machine reboots, that memcopy better have copied the data to some place that I can read it. Now, one convenient thing for me is that while most of those target heap allocations get freed, the target heap itself does not get freed. And the target heap starts with this structure. It's called the heap segment header. And inside of that heap segment header, there is a field that is not used, at least when the VM worker process is running. It's 8 bytes big. And so that's a place where I could copy data and it will persist the VM rebooting. When the VM turns back on, that target heap segment will still exist, and it will have the data that was copied there. So I use this memcopy payload to go and copy data into the target heap, and the data that I'm going to copy there is it's an IAT entry from RPC RT4, and it's an IAT entry for kernel base, for a kernel base function. So this effectively allows me to leak the address of kernel base. So I restart the virtual machine, that address gets copied into the target heap, and then when the virtual machine reboots, the track cache buffer and the VRAM buffer get reallocated. And luckily for me, those bottom-up allocations that are made by virtual alloc are very predictable, right? Because we want to have very minimal fragmentation in the address space. And that means that the track cache buffer and the VRAM buffer are usually going to be reallocated in the exact same spot that they were before. Which means that I can then trigger the bug again. I can do this out of bounds read. And I can go and read the target heap. And I can read that kernel base address out of the heap segment header. I also need to rescan the target heap to find a new VideoDirtListener object, because the VideoDirtListeners all got freed and then reallocated. So I find that new VideoDirtListener object. And now that I know the address of the kernel-based DLL, I can compute the address that the virtual protect function is located inside of it. If you wanted to be a little bit more professional, I guess you would probably go and read the export address table of the kernel-based DLL so that you wouldn't need to have hard-coded offsets, but I didn't have time to do that. Now that I know the address of the virtual protect function, I'm going to create my final payload. What this payload's going to do is it's going to first call virtual protect, and the reason that I can call virtual protect is because it is a DLL export. And by default, all DLL exports are valid indirect call targets. So I'm going to call virtual protect with parameters that I control to make that CFG check function pointer writable. I'm going to use the MemCopy gadget to overwrite the CFG check function pointer with a no-op function. And now that control flow guard is neutralized, I can go ahead and kick off a ROP chain. So I use the relative write primitive to go and overwrite the new VideoDirtListener object with this payload. And I guess it's worth mentioning that this payload was fairly simple. Due to all of the exploit mitigations that have been applied to the VM worker process, any payload you write has to be full ROP. And I didn't really have time to go and create a super complicated ROP payload. And so I opted to do something a bit easier, which is that I just wrote a ROP payload that would go and create a new folder on the hard drive, just so that I could demonstrate that I do, in fact, have arbitrary code execution. I can go ahead and demo this one now. So I'm once again going to run this exploit, but now I'm running on a 1709 host. And the screen is going to shift in a second here, and that's because reading the whole heap takes quite a while with this exploit, and I don't think that everyone wants to sit here for 20 minutes watching this thing scan the heap. So I fast forward. So yep, the window shifts, we fast forwarded, it's almost done reading the heap, and it's presumably going to find the RPC RT4 address, the COM base address, and a VideoDirtListener object address. And it does. So now I'm going to start corrupting that VideoDirtListener object. So it's going to build the payload that will end up leaking the kernel base address for me. That payload has been written, so we need to restart the virtual machine to kick that payload off. All right, so the virtual machine has rebooted now. And then the next thing that we need to do is go and recover the kernel base address that was leaked, and then build this second payload which neutralizes control flow guard and kicks off the ROP payload. So once again, it needs to go and read the heap. So I'm going to fast forward here so that we're not here all day. It finds everything it needs. It finds the VideoDirtListener object. It finds the address of kernel base. And then it's going to go and write this next payload into the VideoDirtListener object. And it takes a little while. The NDR Server Call2 technique requires, I think, around 1,000 bytes per virtual call that you want to make. And my primitive is fairly slow for writing, so writing about 3,000 bytes takes a bit of time because I'm making 3 virtual calls. But I finish writing, and I restart the virtual machine again, and the payload will get kicked off, and I've created a new folder on the C drive, so I have arbitrary code execution. Now, the VM worker process was originally designed with least privilege in mind. However, it was built quite a while ago, and so it doesn't have all of the latest and greatest sandboxing technologies on Windows. It runs with a unique SID, not as the system account or network service, but the SID it runs under is part of authenticated users, so it has access to quite a lot of files on the system. And at the time, it had SE impersonate privilege and a couple other sensitive privileges. And having SE impersonate privilege effectively means that you can automatically elevate to system. So achieving system privilege was a matter of writing a big ROP payload, and I didn't really want to do that, so I didn't. But that's how you would do it if you wanted to. Now let's talk about what we've learned from this, right? Because I said that I wanted to show you how impactful some of these bug reports can be. One of the things we learned is that writing exploits against the latest version of Windows is a lot harder, and also in this case it was a lot less reliable. It took me about 3 days to get the exploit working for Server 2012 R2. And it took me upwards of 20 days to get it working on 1709, which was the latest version of Windows at the time. For 2012 R2, it was about 40% reliable. And for 1709, after 20 days of work, it was like well under 10% reliable. And I'm sure that there are some things that you could do to make the exploit more reliable, but that just means more development time. So you're going to increase that time to write exploit. And I'm personally fairly confident that there's no way that you could make this completely reliable. Things that hurt reliability were, one, since I had to go into the heap, I couldn't corrupt the stack anymore. Sometimes I would run into guard pages, so that would cause me to crash. The other thing was that I now have to run the exploit at least 2 times because I have 2 payloads that need to execute. And every time I run the payload, or every time I try to go out of bounds, I might not find the heap I'm looking for, and I just crash. And so every time I have to do that, it just once again adds to the unreliability of the exploit. And while CFG certainly isn't perfect, because CFG was in place, I couldn't just go and corrupt any arbitrary function pointer that I saw in the heap. I had to go and look for very specific objects in the heap that I could use to build these primitives. And sometimes those objects weren't in the heap, and so I'd have to reboot the virtual machine and look again, and just once again risk crashing looking for these objects that I need. Let's talk about language safety. One of the things that we've been really interested in lately is how we can just eliminate vulnerabilities from our products. And as I mentioned, I had stopped pen testing this component to go and port GSL span into it. And when we saw that GSL span actually killed the bug, that was a great signal to the Hyper-V team and other groups in Microsoft that using things like GSL span is absolutely worthwhile. It can save us from really nasty issues. And in addition to that, the Visual Studio team spent a pretty decent amount of time going and optimizing span for us so that we could use it without risking impacting performance in some of these components. If you look at Hyper-V code today, there is over 200 files that have GSL span being used in them, which is pretty awesome. And I honestly think that a lot of that can really be attributed to this bug report and this exploit that was written, because without that, we would just think it was a cool technology. We've also been doing other work to eliminate bug classes. So we've been aggressively killing uninitialized bugs in Windows. We've been using safer language features in our products. We've been using static analysis like SEML to go and eliminate specific bug patterns in our code. And we've also been investigating just using safer languages like Rust. Sandboxing is another interesting thing to talk about. Virtualization is absolutely the best sandbox that we have built at this point. However, the worker process is designed to run with least privilege. It doesn't need system privilege. And so one of the things that we started investigating after we got this bug report was if it would make sense to go and put the VM worker process in a stronger sandbox, just to add another layer of defense and depth so that you wouldn't just need a worker process bug, but you would also need a sandbox escape on top of that. We've done a lot of work in that area. We don't have anything that's production ready yet, but we do have working prototypes that work for specific scenarios. And we also went ahead and removed SE impersonate privilege and some other sensitive privileges from the worker process in the meantime. And this is once again work that was really motivated by the bug report that we got. Related to that, we've seen that based on the exploits that we've written for this Hyper-V user mode component and kernel mode components in Hyper-V, we can see that the user mode components are a lot harder to attack. The exploit mitigations are more robust in user mode. We have the ability to use safer languages like safe C++ features or Rust, etc. And of course, we do have potential for extreme sandboxing in user mode if we choose to really go through with that. And so as a result of this, the Hyper-V team has been investigating moving some of their kernel components into user mode so that we can take advantage of those benefits more. And finally, as you would expect, whenever we write an exploit, we use that to evaluate how our exploit mitigations are doing in general. One thing we noticed was that this exploit took advantage of indirectly calling DLL exports. And we actually had a feature at the time called export suppression, which prevents that. So we went ahead and turned that on for the VM worker process. And now part of the technique that I used for 1709 is broken, and you'd have to go back to the drawing board there. We also have a new version of CFG that Dave Weston announced at Blue Hat Shanghai called XFG. And when XFG was being worked on, we went and looked to see how XFG would impact this particular exploit. And we can clearly see that XFG would make this exploit substantially harder to pull off because the function signatures would no longer match between the indirect call target and the indirect call site. And we also use this just to look at potential CPU features that we're working on, such as, or not necessarily working on, but just considering as future options. So we might look and see, how would memory tagging impact this? How would something like Cherry impact this, etc. So it really goes and helps us dive into future investments that we should make. So my point here is that your bug reports all matter, and not all of them result in us going and building a full chain exploit for one of our products. But at the very minimum, we use all of this data to analyze bug trends and figure out where we're currently lagging and where we need to invest more. And some of the vulnerability reports and exploit reports that we see are used to drive really big investments in our products. Now, as I noted, we paid $625,000 since last Black Hat in Hyper-V bounties and $4.4 million in bounties total. So please participate in the Hyper-V bounty. We want submissions. And also, please participate in the other bounty programs that we have. I'm out of time. Thank you.